Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at the Fundamental Theorem of Calculus through the lens of using TI technology. I see that many of you are joining us for the first time, so we'd like to offer a special welcome if this is your first T-Cubed Professional Development webinar. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make those tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our two panelists for tonight, Vicki Carter and Pat Flynn. Vicki has been teaching high school math for 41 years and currently serves as the math department chairperson at West Florence High School. She is co-chair of the AP Calculus Development Committee and serves as exam leader at the AP Calculus Reading. Vicki has served on TI-Nspire authoring teams and presented at many international, national, and regional conferences in the areas of technology, calculus, and statistics. Vicki, thanks so much for being with us.
Good evening, everyone. It's a joy to be with you tonight.
And Pat has been teaching mathematics for 23 years. He is currently teaching AP Calculus BC at Olathe East High School in Olathe, Kansas. Pat is a 2013 Presidential Award winner for excellence in mathematics and science teaching. He has served on the TI-Nspire authoring teams and was a writer for the We All Use Math Every Day program in conjunction with the television show Numbers. Pat has presented at many international, national, and regional conferences in the areas of technology, calculus, and geometry. Pat, thanks so much for being with us.
Thanks, Mike. Hello, everyone. I'm looking forward to a really great webinar tonight.
We're expecting a large crowd, so your audio is muted. Feel free to send any questions to Pat or Vicki throughout the webinar using the Q&A window on the right side of your screen. And we may also use the chat window to send general messages. This session is being recorded, and as a reminder, we'll provide a link to the event's certificate of attendance at the conclusion of the webinar. Once that recording is available, if you'd like to follow along with your handheld or your software, and we truly hope you will, we really recommend doing that with the recording. That way you can go at your own pace, pause, and rewind the recording as necessary. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the WebEx menu, choose Audio Broadcast, and then click Join. At this point, Vicki is going to discuss our agenda.
All right, tonight, what we want to mainly focus on is the Fundamental Theorem of Calculus. But in addition to that, we also want to look at the connection to the area function. I mean, there's obviously a connection there. And we are going to look at both some TI-84 activities and some TI-Nspire activities. We'll start with the TI-84 activity that's actually called Fundamental Theorem of Calculus that you can find on the Activity Central for the TI-84. And then we will look at an area demonstration, and then we'll come back to the two math-inspired documents that are on the first and second Fundamental Theorem of Calculus. We'll also take a quick look at a fairly recent AP question and kind of see how it's connected to what we have discussed tonight. In addition to that, we'll share some online resources, and there's also the web giveaway at the end.
Thanks so much, Vicki. And Pat is going to discuss our expected outcomes.
Thanks. So our expected outcomes for tonight are to visualize the connections between the graph of a function and its definite integral, and also explore the relationship between the definite integral and the properties of a function. And hopefully the technology helps us make this quite visually apparent to students.
All right, Vicki, it's all yours.
Okay. Okay, I've got to find the right button here. Share. I know there's a little pause there. So I have a little intro screen here just to tell you that we are investigating the Fundamental Theorem of Calculus. Since this is a connection to AP Calculus and we have our new frameworks for AP Calculus this year, I thought I would spend just a minute looking at the frameworks and where the Fundamental Theorem of Calculus actually occurs there. And Pat and I will just sort of chime in along the way. So, Pat, whenever you've got a comment here, please share. So if you're familiar with the new AP Calculus framework, we have our Enduring Understanding 3.3, which is the Fundamental Theorem of Calculus, and somehow it just jumped. Sorry about that. And we are basically saying there are two distinct formulations that connect differentiation and integration. We have our learning objectives, and then we have our essential knowledge. Essential knowledge is where you should look to know what to teach your students. So if you'll look at EK 3.3A2, there is your classic statement of the first part of the fundamental theorem. If f is a continuous function on the interval AB, then the derivative with respect to x of the definite integral from a to x of f of t dt is f of x, where x is between a and b. You've got some other statements that give connections between the graphical, numerical, analytic, verbal, the symbolic, those kinds of things. There's a little bit more. So on the next part, we have, if you will look at EK 3.3b2, there we have what we classically call the evaluation theorem, which is the part of the fundamental theorem that actually sort of tells us how to calculate a definite integral. There's some other things there about indefinite integral and the statement that many functions do not have a closed form antiderivative. The last EK is just techniques that actually fall under this particular learning objective. And just as a reminder, anything that's highlighted in sort of that grayish blue is actually a BC topic. So those are our framework questions. And so now what we want to do is I am going to move to the TI-84. So, Pat, did you have anything to say about the frameworks as I kind of get this set up?
Not really, but the framework has really been a great help in terms of teaching the class with the students. A lot of times you're wondering, is this going to be on the exam? How is this going to be covered? How does the new exam, because the exam changes this year in terms of communication, for multiple choice parts instead of 5 parts. The framework really helps me focus in as to, okay, what are the specific changes that are going on and how is it being asked differently? It seems like it's really trying to focus in on communicating. Do we understand what we're trying to say and what we're writing? And it's been such a great help with me that the framework has been a huge help with that.
So one of the things that Pat's actually talking about are what we call the MPACs, which are the mathematical practices for AP Calculus, and it would, my best advice to you is make sure you read those and read them often. It's only about a page and a half, maybe 2 pages, bulleted items under each of the MPACs, but they are very worthwhile as far as reading and digesting and beginning to understand. Equally important to the learning objectives. All right, so on this activity, and as Mike told you at the beginning, you will receive a link, and this activity actually is on AP Central that you could find. I mean, not on AP Central, on education.ti.com. Getting my 2 things mixed up there. But you will be able to have both teacher notes and student notes with this, and if you follow along the student notes, it gives you a lot of guidance into actually how to set this little activity up. So basically what we're going to do first is look at what we would call a constant integrand, and the paper suggests that we should graph the constant 1.5. I have already set up the window ahead of time in the way that they recommend, with an x-min of -1, an x-max of 6, and then likewise a y-min of -3 and a y-max of 5. And so I'm going to go to graph, and so of course I see a constant function. Now what we are actually wanting to do is to think about the definite integral from 0 to x of 1.5 dt. So what we're going to do is have the 84 actually calculate these for me. Now, we know that these are going to be rectangular regions, and that's very easy to calculate by hand, but it's kind of interesting to see how the calculator handles this now, especially with the color. So I will go to Second, Trace, which is Calculate, and I'm going to select option number 7, which you will see is an integral there. And so first it asks me for a lower bound. So I'm going to start at 0. So we're going to say the lower bound of our definite integral is 0 and press Enter. And then I'm going to go to 1. So what the students are actually asked to do is to take this definite integral and build a table with x values of 1, 2, 3, 4, and 5. So I'll put in 1, and it actually shades that rectangular region, and of course the area is 1.5. So then they ask them to calculate the definite integral from 0 to 2. And we could just find the area, or we could use this fun thing that we see here, which is number 7. And so now my lower limit is still 0, but my upper limit will now be 2. And so it shades a little bit more, and it reports 3. So,
and Vicki, if I could interrupt real quick, what's great about the calculator is as you can actually see the accumulation happening as it's shading across.
Yes,
it doesn't just magically appear. You can really see it happening.
This is actually, you know, we talk often about the TI-Nspire being so dynamic, but I'm impressed with how this actually appears dynamic as it calculates this area from your lower limit to your upper limit. I'm not going to go through the calculation of each one of those values, but they obviously increase by 1.5 each time. So what the student is then asked to do is to actually put this into a spreadsheet, so a little list. And so I will go to my list. Oops. I will go to Stats. Sorry about that. Edit. And maybe, there we go. And so I'm going to enter in list 1, 1, 2, 3, 4, 5. So this would be the upper limit on the integral from 0 to x of 1.5 dt. And then in L2, I will enter those areas. 1.5, I'm probably going to mistype something in a minute. 3, 4.5, 6, 7.5. Okay, and then we're going to look at the graph of that stat plot. And so I want to turn that stat plot on, and we'll look at the graph. And it's really cool because now the students actually see a linear equation, and there's a lot of discussion that the students can go through, like what is that constant change, and then what's the slope of the line that they can envision here. And this is fairly simple, but the next little part of this activity is to actually change your function now to something like, and the suggested one is to have t divided by 2, which of course that means we need to graph x divided by 2. I have a bad habit of hitting my keyboard instead of the calculator emulator. And I'm not going to clear that stat plot because I'll overtype it in just a second, but we'll see our graph. Okay, so now we have a linear function. And the same thing that we did a few minutes ago, we could calculate and we could find various areas. Or in this case, actually, the students could just do triangular regions and not actually use the calculator. The third example that the students are guided through actually has a function that part of the region is above the x-axis and part of the region is below the x-axis, and I think it's a parabola. And so the students actually begin to get a very visual sense of what's happening with this definite integral. At any rate, I hope those of you who are calculus teachers know what's going to happen here, and I want to move on so that we can see some other activities. But if they were to get the areas from 0 to x of t over 2 dt for perhaps x equals 1, 2, 3, 4, 5, and then plotted in the scatter plot, they would begin to see a parabola, which is really neat for the kids. So now what I'm going to do is actually switch over to the TI-Nspire and show you an activity that is very similar, that is called the area function demo. It says that it's demonstrating the Fundamental Theorem of Calculus, Part 2, and that we have a point P that represents the relationship between X and the area under the curve, and data for the values of point P are collected in a spreadsheet. So if you think about what we just did on the 84, and we didn't do a lot of it, but I think you saw enough that you can kind of get a sense of what would happen. It was a little tedious to collect all the data and then enter the points into the spreadsheet, but the end result is quite an aha moment for students, that they can actually see that function that's representing that antiderivative. What is really nice about the Nspire is that basically they're given, in this case, the graph of a parabola. Okay, point P is right here off the bottom of the screen. So I'm going to grab this open circle, and I'm just going to slowly drag it across the screen. Okay? Now, if you'll watch, up at the top right, you see area. My finger slipped. Sorry about that. You see area, and we see the x-coordinate. And what do you think P is actually representing here, where P is? Think about that. Okay? And so we go to the next page, and instead of having to tediously hand collect a spreadsheet or data, the calculator has collected it for us. And if we go to page 2.3, we have the graph, which is really, really nice. And you can, on this demo, you could change the function. There is a similar activity on the education.ti.com Math Inspired under Calculus that has multiple functions here that you could demonstrate to the students, but this one is just real nice because it's quick and simple. And then you hit reset, and your table is empty now, and you could come back and do the little activity again with another function. So Pat, any comments or remarks there?
No, it really shows how much quicker and easier it is on the Nspire, because it does all that work for you, like gathering all the data, producing the scatter plots. And I know people I teach with at my school, some of the people don't have the Nspire, and I always try to point out to them, you can always download a user license or a trial version for 90 days off the TI site, and that shows students how to do this. And it's a great demonstration just to have this big aha moment, like you said, and like, wow, that's it. It's phenomenal.
So Mike, do we have any questions that we need to address with these two sort of comparable activities, one on the 84 and one on the Nspire at this moment?
I just saw a question from Christine, and her question is, can you help focus on building conceptual knowledge?
I mean, I really believe, see, I've been teaching calculus for a very, very long time. I think this is year 30, and I know that in those first 10 years, there was no way that I was actually, I don't believe I was building the conceptual knowledge because it was so difficult to do a visual. We didn't have these wonderful visuals that the calculators and even other computer programs and applications can do. And I think when a student sees, whether they're doing it on the 84 or doing it on the Nspire, when they see that area accumulating and that connection to the fundamental theorem and what it means with the evaluation part, and then how that builds this new function that becomes the antiderivative, I think it does build conceptual understanding.
Yeah, the visual aspects, I've been teaching for 20 plus years, and we've gone from I had my overheads like slowly reveal the shading happening, and now we've got this technology that really actively demonstrates, almost like an action consequence. Vicky's dragging the open points across and slowly accumulating the signed area as we're progressing through. And it feels real. It feels, wow, that's exactly what's going on. And it helps the students really see that. And visual animation just really, the conceptual part helps so much more with it.
one of the things that I've started doing in my classroom when I use an activity like this is I say capture a moment in this activity and keep it in your mind and connect it to the concept that we're working with now, like the fundamental theorem of calculus, and try to retain that little visual whenever you see those 3 letters, FTC, so that you have that connection.
And we had another question from Mary. She wanted to know if this is specific to non-CAS.
This is, yes. This would not require a CAS unit. So this would work on both the TI-Nspire numeric and the TI-Nspire CAS.
And then Bruce just asked, I'm not sure, this is probably going to change for a lot of people, but Vicki, how much time do you spend on, say, this one particular activity in your room?
Maybe 10, 15 minutes. I mean, it's nice to have some really good discussions, and you don't want to cut them short if it becomes, you know, really deep and they're going somewhere with it. But usually something, and of course, having students familiar with the technology ahead of time makes a big difference so that they, you know, can quickly get into the activity and they know how to drag points and, you know, they know how to go from page to page. So all of those things matter. But at this point, most students would be very familiar with the technology, and this is maybe a 15-minute activity. A lot of people say, how do you find time for that? The value of it outweighs any time that you would spend in the classroom, so it's worth it.
Well, and it saves time later, like when we're finding the integral of various rates. I'll always refer back. Remember that activity we had done when we were dragging the point across and watching the accumulation happening? And they're like, oh, yeah, right. Okay. And they're clued into that visual, like Vicki had said, that moment. And it just makes that part just go so much better because you're connecting it back to this time you had spent on this previous knowledge. And helps that learning progress forward much more efficiently. So sometimes you kind of save much time later on.
I agree with that. All right, we're ready to move to the next little activity. Pat, you ready for Fundamental Theorem of Calculus? All right.
Yes. Okay, so now we're going to be covering the Fundamental Theorem of Calculus. This is where we're basically trying to get to the point across that the derivative of the integral is the functions, right, the first part of the Fundamental Theorem of Calculus. And this is all action consequence. And what's nice about this part of the activity is that there's lots of discussion and students talking about different things. And the great part is it relates really well back to previous knowledge when they were covering F prime and F double prime graphs, finding maximum values, minimum values, critical numbers. It really ties in well with that. So, Vicki, let's go ahead and take a look at the first slide and start. So when I give it to my students, I say, okay, here's what we have. And the upper function is y equals f of x. A is a constant, x is the variable. So x, we're going to be able to change. And we notice down below, we actually have an integral going from a to x. And what I like about the Nspire on this is just to the right of that, we've got the actual numbers from the graph. Whereas in the graph, we see a and x. But it turns out in our graph, a is -3 and x is -1.8. And there is the answer. There is the signed area, the accumulation from -3 to -1.8 of f of x dx. It's 0.801. And so the first thing is just, okay, so want to just grab point x and start moving it around a bit. And they're noticing numbers are changing, and wow, as x is increasing, what's happening? And as we're going across here, usually one student will say, hey, I got 0. Like, okay, well, can anyone get an answer that's 0? And what's nice about this problem is I believe there are 2 locations that give us a 0 in this case. This first one appears to be somewhere around 1.2, and then later on, it comes around right about there. And so then you start asking yourself, well, what does that mean that the accumulation is 0? Gosh, what happens there? It's like, well, something must be going on here. There must be something that's taking place. We have zeros. When critical numbers are 0, we possibly have maximum and minimum values. And that's kind of getting ahead of this activity, but really seeing what's happening with this. And we're going to also, if we change the A value as well, we could verify some other, like our 5 integral rules, right? If we switch the endpoints of the integration, we can see that the answer changes. There's a vast array of things that we can use to connect here. But the big idea is that as X changes, we're slowly accumulating. I mean, whereas on the TI-84, we saw that graph very quickly, here we can slowly grab that point and slowly see that accumulation happen. Vicki, do you have anything to add on this part of this introductory portion of it?
Well, I mean, just this one screen has a lot of power about what you said earlier, the signed area, and getting them to understand that, for instance, that 0 is occurring. Like, what does that really mean as far as, I can't quite get it on 0, but what does that really mean? And some kid will say, you know, well, that must be that this red region above the x-axis and the region below the x-axis, they must have the same area. And so one's positive, one's negative, and that's what's leading to the definite integral being 0. So it's really reinforcing also the second fundamental, the evaluation theorem part of it, where there, you know, what happens when you evaluate a definite integral.
Yes, and so these are creating, like as Vicki has said, these moments, right, of where, okay, capture this in your mind of what we're talking about here and visualize this. So later on in the course, we can cue this video back up in your mind's eye and see what's happening. It is very pleasing because I remember teaching in the beginning, this was a very tough thing to explain. And kids are actually able to see this. It just, oh, it's a nice day. Okay, well, let's go ahead and look at the next slide because we're trying to go ahead and come across at the derivative of this integral, right? That's what we're trying to do here. So what we have now is we've got that same function that we were dealing with in the top half of the screen. But now what we've done is we've, like that activity Vicki had earlier where we were plotting out all of those, we were producing that scatter plot of all the different accumulations, right? So what we have here is same thing we're doing across the top, but now we're seeing live where that accumulation would be at. We're plotting out all of those different accumulation values. We're going to refer to that top function as f of x. And you notice that a of x is being computed as we drag across. And the bottom function is going to be called a of x. That's going to be our accumulation, a for accumulation. Now, we all know that we're plotting out the integral on the lower portion here, the value of it. But what's kind of neat is I'll say, okay, since we've got these two functions here, and let me just ask you, when does, and I usually kind of cover up the screen for a second, and I'll say, okay, when does any kind of function have a maximum value? And they'll say, oh, that's when the derivative goes from positive to negative, or when we have critical numbers or possible locations here, as Vicki has got right here. Well, gosh, the lower function, its maximum value is about right there, and that occurs when the original function is 0. And we're thinking, okay, let's talk back about critical numbers, and wow, when the critical number is 0, our function we're dealing with has a maximum. And it's like, well, that's kind of interesting. And then, of course, once I cue that up, then it starts talking about, wow, when the blue graph is decreasing, so when something's decreasing, we've got a concave down. When we're increasing, we have a concave up. And someone tosses out inflection points. And it's, you know, you spend all that time, about 3 weeks previously, talking about all those concepts. And now we're seeing it again in a different context. And that's what makes the calculus so rich, is that we're able to see similar ideas through different contexts continually. This specific function here is dealt. We're not able to change the function. This is just teaching about it. So let's see. I lost my train of thought here.
Well, let me mention one thing while you're getting your train of thought together. Inevitably, one student in your classroom, if you're showing them this, and maybe they all have handhelds, or maybe they have iPads with the application on the iPads, which it is available, and the kids love to work with the iPads. Some kid is going to say, what happens if A changes? And it is really, if you've never really seen this, this is a really aha moment. So watch the bottom graph if I start moving A. What is happening to the bottom graph? And all it is a vertical shift. That maximum value is going to stay a maximum value regardless of what the value of A is. And so that is very eye-opening for students, and it's honestly not really part of the activity as far as how the students are guided, but it will be a question that will probably happen in your classroom. When my kid says, what happens if you move A? I say, I don't know. Why don't you move it and see?
Right, and again, when we're finding the derivative of an integral, say from 3 to x versus 5 to x versus a to x, that constant value does not change the value of that derivative. It's such a powerful piece that we have here. So hopefully we're trying, and some kid will notice also that, wow, that blue graph, that looks kind of like a parabola, and the lower graph kind of looks like a cubic. I'll bet that red graph is like, it's the integral of the blue graph. I'm like, well, yeah, we are accumulating here. Okay, so we've got all those pieces tied together here, and what we're trying to get to is, I think it's on the next slide, Vicki, where we get to the final.
Yeah.
Okay, so we're trying to build this knowledge back and forth here, trying to see some things. And this one looks like we've just reversed it, but what we really have here is in the top half of the graph, that's our accumulation function. And this is one that they've been going through a lot when we did our whole function on derivatives and applications of derivatives. And below, we're plotting out the value of the derivative. So this should look pretty familiar from previous knowledge, right? F function on the top and F prime on the bottom. And you're like, okay, so F is on the top and F prime is on the bottom. Well, gosh, what happens when F prime equals 0? Or in this case, when A prime is 0? Wow, that's when that's a minimum value for A of x, right? That's a critical number when the derivative is equal to 0. And it just seems like this is kind of almost like this slide right here, this 1.4 is such a big deal to kind of get back to what we had before, because they're connecting to their previous knowledge here. They inevitably wind up with, wow, if we take the derivative of the top function, we get the bottom one. And right away I go to the board and say, okay, derivative with respect to x of A of x equals the blue function. Okay, now what's A of x? So I quickly change A of x to be the integral from A to x of f of t dt, and all of a sudden, wow, there's that fundamental theorem of calculus. And like, well, that wasn't so bad. We've already known that already. And I go, yeah, but you just showed it. You guys came up with it. Now you own this, not me. I'm not giving it to you. You came up with it yourselves. And that was such a big aha moment for the students. We had to kind of like sit down and just look at it for a while. But yeah, and they're like, yeah, of course the derivative of A is A prime. Well, you start filling in what A is, there's our fundamental theorem of calculus. It's awe-inspiring with these students. They see it, and the visualization is built on the connections to them.
And also with these documents, and when we say document, we have what we call the TNS document, which is the one that runs on the calculator or on your computer, which is what I'm using. But you also have a student document and a teacher document, and the student document has some really wonderful guiding questions. And earlier Pat mentioned something about action consequence, and basically what that means is you're acting on this interactive document and what are the consequences of what you're doing, and the students are guided with questions that sort of lead them into good, thoughtful thinking so that they begin to actually deduce what Pat led us to. The teacher document has answers.
Yeah, and great. The questions are phenomenal, and the answers are really helpful to guide yourself on these things. And the use of color on these is great. Like if you notice the tangent line for function A of x is in blue. Well, the graph below is blue because that's the graph of the derivative. Trying to utilize color to help the students see the patterns as we go. Again, I know some questions that people are saying, I don't have Nspire, I don't have this. Well, a lot of these, like this is an action consequence. So I believe, if I'm right, Vicki, there's still, isn't there the Nspire document player that can be downloaded still?
I don't remember. I think maybe, yeah.
I think maybe there is, and that's a zero cost item where you can just you can just download any type of activity that's an action consequence. In other words, grabbing something and moving it and observing the changes. Because both of these activities we've done, we've not inputted any numbers at all or changed equations. We've just grabbed points and dragged them. You can do that. Also, again, I know that at the end of the webinar, Michael's going to talk about how to download or where to go to get the Nspire software as a trial version for 60 days, 90 days. Use it with the students. Even if you're able to use it for a little bit, just one license, one copy to use as a teacher to show students and have them discuss as a class, the visualization is well worth it by far. Okay, I think we've got, I think that was the last slide for that one, I think, right, Vicki?
Yeah, it is the last slide on this one.
Okay. Oh, one thing that is nice, if we can go back to that, I thought of one more thing. If you grab the point A on the top and we move it, like earlier we grabbed A and moved it, right? Well, nothing's happening to our function on the bottom. Earlier, when Vicki grabbed A, it moved it up and down. And you're like, well, what's going on here? Well, the blue graph is the derivative, right? And the red graph is our accumulation. So trying to further get that point across to the students. Great. Okay, so this is our second fundamental theorem of calculus. This is the one that students generally, yeah, that's how I evaluate an integral, and I know that's what we do. Well, let's go ahead and take a look at this and see what happens.
And in all honesty, this one is very similar in build to the other one. It's that the guiding questions that the students have on their handout, it leads them kind of in a different direction.
Right. Like for example, on this slide here, the first thing they're asked to do is, okay, change A to be -3 and change the X value to be +3. And so they do, and okay, that integral gives us a value of -0.6. And then they have the students, okay, now find the integral from 0 to 3. So change A to 0 and X to be, I'm sorry, A to -3 and X to 0. Right. And now we have -1.2.
A to -3.
And X to 0.
Okay.
Right. So, and they have that answer. And it says, okay, without changing anything at all, what would the integral be from 0 to 3? Well, we originally had, from 0 to 3. So originally we had -3 to +3. We just had -3 to 0. Well, if we subtract those two numbers, we should come up with the inner portion. And so we do that in the beginning with this slide, trying to get across, A of 3 minus A of 0 is what gives us our answer here. And they can see this visually that, yep, that's exactly what comes out. And we're like, yeah, it's adding numbers, right? This piece plus this piece should equal the whole piece.
And something you said earlier, that this gives actually those properties of integrals, properties of definite integrals, a great visual way of sort of understanding them.
Yes, absolutely. And so what the student activity does is it has them go through, I think, 5 or 6 pieces just like that, taking a look at this and seeing what happens. Okay, so now what we'll do is we'll go ahead and look at the next slide. And again, it looks like Vicki said, it looks very familiar. We've got our function at the top and we've got our accumulation in the bottom. And we're, again, moving points left and right, noticing what happens. And again, we ask students, well, what do you notice here? What's the relationship, if any, do you notice between the original function on the top and the accumulation function at the bottom? Well, it appears that the blue function on the top is a derivative of the bottom function. Earlier we had talked about when function A is concave up and F is decreasing. All those pieces that we had done earlier, we would again talk about here as well. Okay. But the big idea here is we're still hitting the same pieces, right? Noticing when we have critical numbers, when are the critical numbers equal to 0? When is the red function decreasing? What do we notice about the blue function? And trying to get those concepts across. But what we're trying to get to is how we go from one piece to the other, right? How we're getting to that second fundamental theorem of calculus. So on this page that Vicki is on, students are basically asked finally at the end, give your response to the following question. F of x is blank of a of x. Now, f of x is the blue function. That would be the derivative of function a of x. And then that would mean that a of x is the antiderivative of f of x.
And that basically gives them the method that they would use to evaluate their definite integrals.
Absolutely. And so then later on in this activity, it guides them through some other integrals as well. Please evaluate this. With my students, it's generally the Fundamental Theorem of Calculus part, or they call it part one, but the first part of it. That's the part that they need a lot of help with. The second Fundamental Theorem of Calculus, it seems like they've already been evaluating integrals this way already before we get to it for some reason. I'm not sure what your experience is with this, Vicki, but my students, it's the first portion is definitely more of an aha than the second portion because they've already been doing the second portion,
yes.
so to speak. They're not really sure what they're doing, maybe. Maybe that's the part.
I think they have a very difficult time getting their head wrapped around the fact that we're defining a new function in terms of a definite integral. Whereas just that concept of, oh, I've done thousands of derivatives, now I'm going to think about doing a derivative backwards. Oh, I can do this. I've got something sort of solid to wrap my head around on that. And I think that's the difference.
I agree. And then the AP, when it's assessed, is very interesting. I don't know if we want to move on to the AP question on this, or do we do an 84?
Things. I don't know that we'll actually get into the 84. I just wanted to kind of mention what I do when I'm teaching. So I didn't start this as an actual PowerPoint, so suppose you didn't see this bottom part. The way I actually, before they do actually do the evaluation theorem, I build a lot around geometric formulas for area, like triangles and rectangles and trapezoids. And so I might give the students, let me just start as PowerPoint so it looks better. So I might give the students this kind of a problem where I'm saying, okay, this is just the graph of f of x. And see that little thing popped up. I didn't want it to. And so just evaluate these definite integrals. So actually we're just doing pieces. We're doing chunks. So we do this triangle, we do this little triangle, we do the area under that little constant function, and then we do this little trapezoid. And we talk about it. And then I start saying, kind of building that accumulation idea. Well, what if I wanted the definite integral from -2 to, instead of +2, go all the way to 3, or -2 to 5, or what if I wanted -2 to 8? Well, they begin to see that it connects to those properties. So this is that, adding adjacent sections and getting the integral of the big section. And so they really attach to that. They understand that. But then you go, well, wait, what if I now define a new function as g of x, and it's the definite integral from -2 to x of f of t dt? So if we had 2 hours here, I probably would have actually let you compute maybe g of -2, -1, 0, da-da-da-da-da, all the way to 8, and we'd plot it, and we would see some really neat little features of this antiderivative. And it could easily be done with that scatter plot on the TI-84. And so I would do something like this if I were using the TI-84 in my classroom. And then the neat thing is you can bring in now the first part of the fundamental theorem, because you can say, okay, well, what is g prime of x? And if they understand the first fundamental theorem from some other things that you've done in the classroom, they should know that it's f of x. So you could ask them for g prime of, for instance, maybe g prime of, let's see, 2, 3, 4, 5, maybe g prime of 6, and it would actually just be f of 6. And then I love to ask them, well, what would g double prime of 6 be? And they go, well, now you're making it hard, Miss Carter. And they say, okay, that's f prime of 6. And then it's like they've forgotten everything they ever talked about with the derivative, because they're in this new world. And you go, what is the derivative? And someone will finally say, oh, it's the slope of a tangent line. And you go, well, what is the slope of that segment? And so it really starts tying back into the use of the fundamental theorem with prior knowledge, and yet you're also working with this definite integral and sort of getting into that accumulation idea. So it's a nice transition. And then Pat and I want to just spend a very quick moment with you on an AP question. And we do not want to go over here, but we'll take just a few minutes here. This one is from 2014. And if you remember this year's exam, 2016, the students were given a curve that had, I think it was all piecewise linear, but they were not, the function was not defined as an accumulation function, as a definite integral. It just said, here's the graph of G prime. And students had a little bit more trouble. So we've learned students have more trouble getting into that problem than they do when we actually define it like this as an accumulator, as a definite integral, which I thought was interesting. So in 2014, first thing they asked them to do was find G of 3. So basically, that's 2, that's 3. So they're basically accumulating area from -3 to +2. Now, they had to figure out that at +2, this thing went down to -2. So this point was 2, -2. So they found the area. Basically, it ends up being 9 because this is a triangle with an area of 10, and this has an area of 1, but since the region is below the x-axis, then the net area would be 10 minus 1, which is 9, and it was only worth 1 point. But the interesting thing is the rest of the question. And Part B is focusing on analyzing that graph. And so Part B says, on what open intervals contained in -5 less than x less than 4 is the graph of G both increasing and concave down? Give a reason for your answer. I'm going to tell you people that the minute students see a problem like this, they see a function defined as a definite integral. It is almost an absolute that somewhere on their paper they've got to make the connection through the fundamental theorem that G prime of x is equal to f of x. I tell my students, give the reason before you even start the problem. Go ahead and put it up front. Go ahead and say, I am smart, I know this, and now I'm going to use this. And it will really benefit them if they have actually made that connection between G and F. Now, I'm not going to go into the points for Part B. I want you to look at Part C. So Part C defined a new function, h of x, which is g of x over 5x, and they're asked to find h prime of 3. As we all know, the process of finding this derivative is a quotient rule, and within that quotient rule, there would be a g of 3 and a g prime of 3. Now, they found g of 3 in Part A. They need g prime of 3. It comes from that connection again, the fact that the derivative of g is f, and I'll go back to the graph, and do you remember me pointing out to you that at 2, this point would be 2, -2, so g prime of 3 would be, g prime of 3 would be -2 because it's f of 2, which is, f of 3, which is -2. I'm getting my 2's and 3's all mixed up here. So they would have, they kind of had already found that point or kind of thought about that point when they found g of 3, but they really need to know what the coordinates of that point would be in order to get their, to get credit for evaluating h prime of 3. On this question, this was worth 3 points. Part C was worth 3 points. 2 points for actually carrying through the quotient rule correctly, and only 1 point tied in to pulling all of those values together and replacing the symbolic pieces like g of 3 and g prime of 3 with numeric values. So that was the third point. But these are the kind of questions students are going to see.
Well, I thought it was brilliant with Vicki was showing earlier before we got to this question. She was asking students, well, what would the f prime of this equal? What would f double prime? Oh, that's the slope of the tangent. All those ideas are included right within that question, and she was trying to assess that with the students earlier in the previous question. a lot of times on this one, my students did really well in Part A, but when they get to Part B, like you said, it's a totally different context. They don't know what's going on. And you say, well, how do you know when a function is increasing? Well, that means G prime is positive. And you say, well, what is G prime? And then it gets back to that connection that you had just said. But it's tying that knowledge to the previous stuff they already did really well on, but now it's in terms of an integral, and they have to repeat that learning again.
Which is good.
Yeah, exactly. I mean, what's nice is if you can pull back to it and tie it to previous knowledge, it makes it so much better for the students to see it, and they start seeing these great connections within it. And then the visualization that we have with all of the software really makes it much better for students to see things.
Mike, do we have any questions we need to address?
I haven't seen any recently.
Okay.
All right. Well, this question is on every exam. It has a question just like this, I believe, right? I mean,
yeah, they're
I'm
usually
pretty sure.
They're either piecewise linear, and I do tons of these with my students. They're like pieces of lines, quarter circles, semicircles. And the students really need to get used to using that. As a matter of fact, I used one on a test the other day, and it was the semicircle that had been moved up, so the semicircle was sort of up here, so they actually had to get the area of the rectangle minus the semicircle to have the two little pieces underneath the semicircle. So they really do need a lot of practice with this area geometry, area connection to the definite integral.
Right.
But what I have found out is some kids can't leave the geometry, and then when they start seeing parabolas and they keep going back to like the Riemann approximations, it's like they're so attached to the geometry sometimes they lose what the meaning of the calculus is. And then I think that's where something like the Fundamental Theorem Nspire activity really helps kind of bring them back around full circle to make that area connection and what's going on and how that definite integral relates. So it gives them that movable piece that they can visualize.
Absolutely. Oh, yeah, we do a lot of geometry ones in the beginning, as you were talking about semicircles, straight line segments. I love giving them absolute values in there. I haven't thought of it elevating above the x-axis, so that might be one for tomorrow's class. That's really good. But again, the more connections we make within the learning, the better it is for the students to see it. It's not like there's an infinite rung of ladders to climb through calculus. It's similar topics that they keep seeing in new and different contexts, and the better they know these concepts, the better they're going to do when they see it within a new context.
Yeah.
This one here, this question here, all it has is once you make that connection point, it becomes something from application of derivatives. Once you've made the connection that G prime equals f of x, that's now it's application of derivative question, which they did really well just a month or so before you got to this topic. So it's just giving those kids those success moments and making sure they understand what's going on. Mike, there's more questions, I guess. Is that right? Oh.
Okay. Mike, are you ready for me to turn it back over to you?
That'd be great.
All right, here we go.
Thanks so much, guys. As we begin wrapping things up tonight, if you do have any last-minute questions for Vicki or Pat, please try to get those asked. I know they'll do their best to get those questions answered.
Well, I see somebody said one of my areas might be wrong. It could be. I changed my function at the last minute, so I might not have corrected one of the areas.
No problem. When you leave the webinar, a brief survey will automatically appear in your browser, and your feedback guides us as we plan future online events. So we really hope you'll share your thoughts in the post-webinar survey. We're excited that this year's T-Cubed International Conference is coming to Chicago, and it's coming up quick, early March. I know I'll be there. I'm pretty sure both Vicki and Pat will both be there. I know I'll be presenting, and I think there's a good chance that the two of them will as well. But I just wanted to take a minute and share my personal thoughts on what makes the conference special to me. I've been going since 2008. I haven't missed a year. And each year I always get to reconnect with people that I haven't seen in the past year, but make new friends and new connections. And I can't tell you how many times throughout the year it's been helpful that I'm in the middle of teaching something, or I'm planning a lesson, and I get stuck with something, or I've met someone that just I know creates some really amazing things, and I can just reach out to them and say, hey, Pat, I'm teaching the Fundamental Theorem of Calculus tomorrow. Do you have anything really, really slick, or how do you teach it? And so for me personally, I always make some really great connections at these at the T-Cubed International Conference. So I think everyone's takeaway may be different, but that's mine. Pat, do you have anything special that you feel about the conference?
I think Pat went silent, went mute.
Well,
I'll speak up right quick. Oh, there he is.
Sorry. Go ahead, Vicki.
No, I was just going to say the conference is just every year I learn something, and I've been teaching calculus a long time, and I've accumulated a lot of knowledge to have a little fun there. But I learn something valuable every year, and it's just so great to connect with other people. Another thing is it's great to hear other people have students that fall and that have the same stumbling blocks, that fall in the same traps that your students are, and it kind of gives you a reassurance that what you're trying to do is the right thing. So it's a great professional development.
Right. Well, and the best thing I've always thought was everyone I see there is the most humble person. I mean, like I've got the same error you do. I remember talking to Mike Kaler about trying to teach converging sequence and series, and my kids aren't getting it. And Mike's been teaching calculus forever. And he's like, Pat, they always have the same trouble. This is a tough topic to talk about, and I always stumble every year with it. Here's some new things I've been trying, and you always see these people that you think that you read about on AP Central, like Vicki and other people, and like, you know what, my students have the same issues. I'm trying something new. What have you thought of? And it's just such a great way, like you guys said, to make connections with other people and learn new ideas. And often at times you're like, wow, I forgot to go to lunch. It was such a good conversation about something I forgot to eat. And you'll be doing things till 8:30, 9 o'clock at night, learning new techniques, and you come back and, God help your kids in classroom, because they know come back from a conference, they're going to be doing lots of new and exciting stuff and working pretty hard. It's a great way to learn lots of new ideas. I've enjoyed every year I've gone. No doubt.
Well, earlier Vicki mentioned that tonight we have a webinar giveaway, and the webinar giveaway tonight is a T-Cubed International Conference registration, free registration, and tonight's lucky winner is Conrad Wilberg. So Conrad, congratulations. We'll be in touch over email over the next couple of days to give you a little more information, but we really hope to see Conrad as well as everyone else at this year's T-Cubed International Conference.
Congratulations, Conrad.
Yes.
We'd love for you to continue the conversation on any of the major social media outlets. If there's some things that you saw tonight that you're really excited about, please feel free to communicate those on social media. To receive a certificate of attendance, go ahead and click that link in the chat window. Also listed is a link for the documents that were shared tonight. If you happen to miss either one of those, or maybe one of them isn't working for you in your browser window, have no worries. You'll automatically get a follow-up email within a couple days, and then that email will be a link to the recording, a link to the certificate, as well as a link to the documents. If you happen to be watching this on demand, please feel free to copy down the certificate link into your favorite browser, and you'll receive your certificate. If you need a post-webinar follow-up, feel free to give us a call at 1-800-TI-CARES or send us an email at ti-cares@ti.com. Thanks so much, Pat and Vicki, for everything you shared tonight about the Fundamental Theorem of Calculus. I think we got some positive feedback so far already, so again, thanks so much for everything that you shared.
Thank you, Mike. It's been a great evening.
Yes, it has. Thank you very much, everyone.
Thanks again, and we hope to see everyone back online real soon. Have a great night.